Right after class today, I will activate the quiz. Quiz 4 will be activated. Right after class today. And it's due Sunday night. Exam 4 is on Monday. Then on Tuesday, I will be teaching 12-1 and talk about exam. Wednesday, exam practice. Maybe starting some exam practice on Tuesday, if you have to. That's Wednesday. Okay. And Thursday is the final. That is also the due date of the project that I hope you do it as soon as possible. Do not leave it for that date. Okay, that's the general idea of what we're gonna do for the next few days. So we have today and 4 more classes next week. Which 2 out of 4 will be exam time. Okay, any question before we start it? Okay. Go to the canvas of the course. Modules. Eleven one. We're going to talk about goodness of fit test. In your calculator, how many of you have TI-83 calculator? So maybe before I get it started, send me private chats if you have TI-83. TI-83. Let's see how many people. 3 so far. 4. Okay, those of you who have TI-83 calculator, you need to follow the third step. The third one is when you write the program for your calculator. It's a goodness of fit test. Those who have TI-84, you have the goodness of fit test, but for TI-84, but for TI-83, most of them don't have it. So you need to write the program. That's why you need to follow step 3. So let's just get us started, and then maybe after class you write the program and then ask me questions, or or I'll stay and let you write it, but it's a short video that you play. I don't know how many minutes. It's 8 minutes. Maybe during the break that I give, you can write it down. So, but, and then also this video. So let's just go to the PowerPoint. Oh, okay. So it's just 3 calculator. But anyways, I'm gonna give a break so you can. Okay. So two things. Chapter 11 has only 2 sections, and we're gonna cover both today: goodness of fit and contingency tables. So let's look at this one. By goodness of fit, we mean that the sample data consisting of observed frequency counts arranged in a single row and column called a one-row frequency table agree with some particular distribution, such as normal or uniform, being considered. So we will use a hypothesis test for the claim that observed frequency counts agreed with the claim distribution. So this is gonna be our hypothesis testing it for this section. And I hope you add it to the list of other hypothesis testing. So always for this one, null hypothesis, alternative hypothesis. So we would say that we will use a hypothesis test that observe counts agree with the claim. So that would be, so you're gonna have some observation. So let's just go to one example so you see how the claims work. So you're gonna have some observed and some expectations. So when you're rolling a dice, you give 1/6 chance that you roll 1, 1/6 chance that you roll 2, and so forth. That's your expectation. But when you are actually rolling it, you may see something else. Your observed may be different than the expected. So we're gonna fill in the expected together. But when you want to write the claim, let me just bring okay, here we go. So with the null hypothesis, you would say that everything is as expected. And then with alternative, you would say at least one probability is different from others, means being different than what expected. So observed, different than expected. And then observed, same as expected. Okay, so I want you to write this null hypothesis, alternative hypothesis down. And then I'm going to go back to definitions. So by the end of this section, we're going to write null hypothesis alternative that probabilities are the same as expected. And then alternative would be at least one probability is different from others or from the expectation. You can always use words too. say probability is the same, at least one probability is different. Okay, so let's go back. To the first page. Okay. Goodness of fit test is used to test the hypothesis that an observed frequency distribution fits some claimed distribution. So observed is fitting some claimed distribution, and that's the goodness of fit test that we're going to do today. If you want to take a moment to read it and then maybe write a note, because that's our lesson for today. Okay, conduct a goodness of fit test, which is a hypothesis test to determine whether a single row or column, just single row or column of frequency counts agree with some specific distribution. So that's our objective for today. Again, you're going to make some claim, and then you're going to observe, and you're going to see if these two are matching. So that's the testing. You claim that your expectation and your observation agree. Okay, please write these symbols. They are pretty new. O is for observed frequency, means you have some expectation about flipping coin. So you flip coin and you're expecting that out of two, one be head, one be tail. So your expectation of flipping coin is 1/2 head. Means if you are doing it 20 times, you are expecting 10 times head. But then this is your expectation. Your observed might be 16 heads when you're actually observing and 4 tail. So that's observation means. Observation means actually observe it. And expectation means what do I expect? Okay, K is the number of different categories. N, number of trials. P is the probability. So please take a quick note of symbols because we will be using them. Okay. For goodness of fit test, the data should be randomly selected. Sample data consists of frequency counts for each of the different categories. For each category, you should have expected frequency at least 5. Um, so whatever is your expected should be at least 5. So when you are rolling or where you're flipping coin out of, let's say, you are rolling it 30 times, you are expecting, so you're flipping coin 30 times, your expectation is that 15 times head. If head is your favor, your expected should be greater than 5. We don't care about observed. Observed could be greater than 5, could be not. But our expectation to begin with should be at least 5. Okay? Null hypothesis, alternative hypothesis. You would say that the frequency counts agree with the claim distribution. The frequency counts do not agree with the claim distribution. So that's pretty much for all of them. You can write them in P and others, but then you can always write it for goodness of fit test. The frequency counts agree with the distribution. So please make sure in one side of your note, oops, in that page of note that you dedicated to calculator commands, write this out. The frequency counts agree with the claim distribution. Okay.
Hold on, Professor, you mind back a slide?
Which slide do you want to go?
Oh, wait, sorry. I thought you just need more time to write the last bullet point down.
This one or the, hold on a second, sorry, the dog is barking. Hold on a second. I'm sorry, go ahead, please.
I just needed more time to write the last bullet point down. I just thought you switched the slides.
Oh, this one is fine, or you want me to go to the previous one?
Oh, this one's fine.
Let me let my dog out and come back so you write this null and alternative. Okay, so let's now go to find the p-value. In order to find the p-value, we're going to use our calculator. We're going to use technology, so don't worry about critical values at all. Okay, and you don't need the formulas. Okay, let's just work on this problem. May I ask a volunteer to read the first example here, part A. Equally likely. Anyone?
I'll read.
Thank you.
A single die is rolled 45 times with the following results. Assuming that the die is fair and all outcomes are equally likely, find the expected frequency E for each empty cell.
Thank you. So it's rolled 45 times. Out of 45 times, so 45 is a number that it's not exactly divisible by 6. Let's say if it was 42 times. If you're rolling a die 42 times, how many times are you expecting to see 1? How many times are you expecting to see 2? And so forth. How many times? Let's say you're rolling it. I'm just changing the question in a way that it's first easier to calculate. Let's say you roll the dice 42 times. How many times you're gonna see 1 or expecting? How many times you're expecting 2? How many expecting 3? And you know a die has 6 sides. How? Out of 42 times. How many times for each category if there were 42? If you were rolling it 42 times. Let's change the question. If you're rolling a dice 6 times, how many times are you expecting to see 1? Or 2 or 3 or 4? Great, 1 time. If you're rolling a die 12 times, so you're rolling it 12 times, how many times you're expecting to see 1 or 2 or 3 or 4? 2. Great. So every time you are dividing by 6 and you say, my expectation is that if I'm rolling it 6 times, I would see 1 time, 2 1 time, 3 1 time, and so forth. So in reality, you are dividing it by 6. So if you're rolling it 12 times, then you are dividing by 6 and you say, I'm expecting to see 1 twice, 2 twice, 3 twice, and so forth. If I'm rolling it 18 times, then I'm expecting to see each of them 3 times. If I'm rolling them 45 times, I know it's decimal, but we use decimal in expectations. So you are expecting 7.5 times with each of these. Okay. If you be able to fill in, so observed is given because you must observe it. Expectations in majority of cases is something you need to find. So in L1 and L2, so in L1 put 13, 6, 12, 9, 3, 2. In L2 always put expectations 7.5, 7.5, 7.54. So let's do that. And those of you who have TI, so do this part, even if you don't have the command later, but do this step with us. Okay. So let's just write the null hypothesis, alternative hypothesis here. So step 1, null hypothesis and alternative hypothesis. So that's our first step. So null hypothesis is that the expectation and the observation match or are the same. Alternative hypothesis is when expectation and observation are not the same, or at least one is different. Okay. Step 2, requirement says expectation at least 5 counts. In this case, expectation was 7.5, so it is greater than or equal to 5, so checked. Now we want to find p-value. So let's go to our calculator. So go to L1. And L2. So in L1, put observed 13, 6. You were rolling it 45 times, so and observe these. If you add these up, you're going to get 45. 9, 3, 2. You were expecting it to see 7.5 times 1, but you saw it 13 times. At the end of the day, you want to know even if this die is fair. If it's way different from the expectation, then it's probably unfair die. Means it's likely to roll on one side than others. So 7.5, 7.5, 7.5, 7.5, 7.5, 7.5. Okay. So now you go to stat, test, goodness of fit test. Do you see D? Chi-square goodness of fit test. Observed is in L1, expected in the L2. Degree of freedom. So you had 6 items. Degree of freedom is always n minus 1. So what you need to put for degree of freedom is n minus 1. So it means you had 6 categories, 1, 2, 3, 4, 5, 6. So minus 1. Or you can say this, k minus 1 category. So that's 6 minus 1 is 5. So expected is 5. Okay, so you go down, you calculate. Here is the p-value. So let's write down the p-value exactly like before. If you are comparing with 5%, this is less than 5%. So we reject no. No was that they are the same. And you support alt. You support that this is unfair. This is at least it. One of them is not matching the expectations. Support alt. So we would say we have enough evidence to support instead of saying that the expectation and observed are not matching to support that the die is unfair, because our expectation was not matching. You're supporting alternative, and alternative was saying that they are not matching. If they are not matching means the die is unfair because expectation is significantly different than observed by the p-value. Okay, any question? So I noticed that three of you, did you get the calculator command?
No, I wasn't able to get it. I have a TI 83.
Yeah, one more time. Those of you who have 83, do you want to write the program now or you want to write it after class? So I can give you like 10 minutes, and then you follow the video and write the program. Just send me a private chat that if you want to write, if you have TI 83, do you want the time now to write the program or you want to do it after class? Okay. So let's just, so those of you who have TI 83, one more time, tell me who you are, so I can help you with writing this program while everyone else takes like 10 minutes break. Okay. So let's go to the video because I would teach it off of the video too. I mean, I would do the same thing as this video would do. So let's just.
But not all TI-83 and TI-84 calculators come with.
Do you hear me, or do you hear the video?
I can hear both the video and you.
Okay, so I'm gonna let you look at the video. What if I give you? Okay, let's do this. I'm gonna give you 10 minutes. Play the video on your side, mute yourself, and then I'm gonna give everyone 10 minutes break. This is 8 minutes, 9 minutes video, and try to put it into your calculator. And then I'll help you after that. So you start off
A pre-programmed
by going
goodness of fit
to.
test. To see if your calculator has this pre-programmed test, you can go to Stat and then scroll twice to the right to Test, and then go up and see if chi-squared GOF test is listed, like it's listed here as option D. It should be option D in your test list if you have it. If you don't have it, don't worry. We're going to, right now, write a program for our calculator to do the chi-squared goodness of fit test for us from scratch. So second quit to get back to home. To write a program, we will go to Program, PRGM. We will scroll to New, and we will press Enter. We're going to name our program chi-GOF. And right now the alpha is flashing, so that means our alpha is locked. So we'll just choose the green keys, C, H, I, and then G, O, F, enter. And now.
Okay, so I want you to keep going, keep watching the video on your side, mute yourself, watch the video, try to write the program, and then we'll work together. So I give you 10 minutes here. And everyone else, take a 10-minute break. And I am here to help you if you need me. Observe the L1, L2. Degree of freedom again is 5 because you still have 6 categories of rolling dice, one less, it's 5. And that's a very small p-value. So this is a very small p-value. It's e to -4. That means you go backward 4 places. So it's 3 zeros to 8. So 0, 0, 0 to 8. That's a smaller than 5%. So reject and all. Support alt. So that means this is not, so there is not enough evidence to support that the new model would work too. So that support that the distribution is different. Oh, actually, sorry, we are supporting alt. There is enough evidence. What do I do? There is enough evidence to support that the distribution is different than 50%, 10%, 50% for one, and 10% for others. So there is enough evidence. We are supporting alternatives. So there is enough evidence to support that the distribution is different than 50%, 10%, and others. Because alternative was, so null is the equality. We said that it's equal to 50% or as we expected. Alternative was different than expectation. So you would say we support that is different than our expectation of 10% and 50%. Any question? Okay, let's go to okay, they use the formula, so we don't need to use it. So this is a small table. The test statistic, instead of t and a z that you had in the past, is chi-square. So we read it as chi-square. Chi-square. And so large chi-square is associated with a small p-value. Small chi-square with large p-value. So exactly like large t with a small p, large z with a small p, same thing, large chi-square, small p. So we reject a null if p is a small, and then not a good fit with the assumed distribution. So in this case, we rejected the null, so it was not a good fit with 50%, 10%, and so forth. Okay. So let's go to the textbook now. Textbook has good examples that we can go over some of them. So pull my MATLAB up. Go to my MATLAB. So pull the textbook up. Homework for 11.1 and 11.2 will be due on Sunday night. I changed the due date if it says otherwise. Go to 11.1 homework. Okay, so let's do number 15. I'm gonna give you 5 minutes. Read the question. It's World Series games. There is observation of World Series contests. And there were some expectation proportion. Remember, there were 100 major leagues, so you need to multiply each of these by 105 to find the number of expected. Exactly like when we were multiplying decimal with percentage, with like 45 with 50%. So you need to multiply that by the fraction because that's like a proportion as well to find the number of expected. So you are expecting 2 out of 16 of them to be the number 4 category, and then 4 out of 16 of them in the number 5 of game played category. Okay, so put them in L1 and L2 and then see if you can do it. So I give you a few minutes. Okay, so let's just put that in L1. So in L1, 21, 23, 23, 38. And then since decimal is okay in L2, you can just put it 2 out of 16 times 105. Just type it right here. You don't have to do it separate. And then 4 out of 16 times 105. Five out of 16 times 105. And then same thing for the last one. 5 out of 105 out of 16 times 105. So keep in mind that the null hypothesis is always saying that expectations and observation and matching. So our expectation were same as what we observed, and alternative would be they are different. Okay, now you go to stat to test. You go to goodness of fit test. Things in L1. How many categories you had in here? 4, I guess. Was it 4 categories? So then you go 4 minus 1, 3. So you always put 1 less than the categories. So you put 3, and here we go. So that's less than 5%. So we have enough evidence to support that the number of game played and the observation are different. So observation, which would word you would say based on the games, and expectations are different. Because alternative is always that they are different, and null is always that they are the same. So in this case, you would support the alternative, reject the null, support alt. If you are supporting alt, supporting that they are different, because alt is always different. Okay, any question? So I hope you get an idea of what to do. So anytime you have observation and expectation, that's what you do. So next section is about, so 11.2 is more than one row. So let's open that, and I'm gonna give you a couple of minutes of walk around and come back to this. So let's go to 11.2 modules. That's contingency table. I put 2 videos here for you to observe. Everyone has the calculator command for this one. The idea is very close to what we had done with the previous one. So it's arranged in a table that has row and column instead of just row. And we present the method of conducting hypothesis test of null hypothesis that the row and columns are independent of each other. So when you come back after 5 minutes, so I'm going to tell you that null hypothesis. So we have null hypothesis and we have alternative hypothesis. Null hypothesis says that the row and columns are independent. So you're going to see through examples what that is. And then what is the alternative of independent? Then would be dependent. So row and columns are dependent. And that would be for the entire two-way table. So the same thing you always write for the null hypothesis and alternative hypothesis. So null is always that they are independent of each other, and alternative is that they are dependent. So take a 5-minute break. I want you to get a little bit of walk around and then come back. And it's pretty straightforward, easy to do this one. So 5 minutes, it starts now. What time is it? 10:26. Be back by 10:31. Okay. Test of independence. The null hypothesis is always saying that the row and columns are independent. So null hypothesis, row and column, independent. Alternative hypothesis, row and column, dependent. Please write it somewhere as we use them throughout the lesson. Okay. So we're going to just test a hypothesis. So pretty similar. O is observed frequency, because for this one, same thing. You're going to have observed frequency and you're going to have an expected frequency. R is for rows, represents the number of rows, like how many rows you have. And C is the number of columns. Again, for this one, the expected should be at least 5. You don't care about the observed, but what you're expecting should be at least 5. Okay. Null hypothesis alternative, we talked about it. So let's go to an example. So same thing as before, if you get chi-square large, p small, then you reject the independence. So there is enough evidence then to support that it's dependent. So if exactly like before, if you get a small p-value, you reject the null and you support alt. In this case, null is independent, so you reject the independence if p is small, and support dependent. And same thing with fail to reject the null. You fail to reject the independence and you do not support the dependence. Okay. The nice thing about calculator is you put in the expected, you put in the observed, and it's gonna come up with the expected most of calculator on its own. Let's give it a try. So here is success and failure of surgery, weight bearing cast, non weight bearing cast for 6 weeks, not weight bearing cast for less than 6 weeks. So you want to know if success and failure is independent of the type of procedure they do. So you want to know if the success and failure are independent of the procedure they do. So, and what do you have? I'm going to just write it nicely here. You have 54. You observe that 54 surgeries were success, where 12 surgeries were failure. 41 surgeries, weight bearing cast was success, 51 not. 70 non weight bearing for 6 weeks was success, 3 not. 17 less than 6 weeks was success, and 5 not. So this is just given. Forget about the expected. We don't calculate it. It's going to calculate it for us. So write down or take a picture of this one as I show you where you're going to enter it. So this is the observation of how many success. Can you read the table? Like surgery, 54 success, 12 failure, and so forth. You want to now know if, so here is your null hypothesis, success and failure are independent of type of procedure. And then alternative, you're going to say that they are dependent. Means success and failure is dependent to the type of procedure. So write down these numbers. Let's go to our calculator. And now everyone has this command. So what I want you to do, and it's also on the video, I want you pay attention to this. Maybe you didn't see this key before where you enter the values. It's under second matrix. Because it's two-way, you need to enter it in the matrix. See what I highlighted in red? Second, the red. Second matrix. Do you all get that? Then you want to edit that one. Oops. So you go second matrix. You want to go edit the matrix. So you're going to scroll to edit. Then you're going to say, so they are asking you, what is the size of the matrix? So size of the matrix is row times column. There were 4 rows here and 2 columns. If you do them correctly, you will see exact size that you need. So 4 by 2, row times column. So you put the number of row first and the number of column. So this is the horizontal. So how many of you have? 4 of them. And then column is the one that are vertical. So you have 2 of them. So you have 4 of the horizontal and 2 of the vertical. Okay, let's put it in. 54, 12, 41, 51, 70, 3. You just enter them as you see, 17, and 5. Did you all enter that? And what is the question more time? So you go to second matrix. Did you get that part? And then you go to edit. You click on A. You're trying to put A as a 4x2. So you type 4x2 and then you put the data. Is that clear? Okay. So now, I hope you all got that part. You go to stat. You go to test. You go all the way down to chi-square test. It says observed in A. Expectation, they're gonna automatically write the program and put it in B for you. Then you go and calculate. So now do you see the p-value? This is a small p-value here, less than 5%. This is almost zero. You go backward 12 places and you put zeros for all of them. So we have enough evidence. So you reject a null, support alt. We have enough evidence to support the claim that so dependent were my alternative. So you are rejecting the independence because you are rejecting the null. Support that surgery, success and failure are dependent because you're supporting the alternative was dependent, are dependent to the procedure, to the type of procedure. Okay. And as you may see, if you go to second matrix, do you see they already developed B themselves? So this is what you see on here that they calculated for expectation. The calculator will calculate that for you. So you just enter A as of second matrix. And then once you enter A and go to chi-square test, then it's gonna develop B for you. Okay, so that was it. So that's what you need to do for this section. So let's do another problem. We can use our textbook for it. Yeah, let's just go to the textbook. Go to page, let's say 500. Oops. 500, maybe 59. So let's look at number 16, injuries and motorcycle helmet color. Can Can someone read number 16 and then we're going to put it in our calculator and know if they are independent or not? May I have a volunteer to read number 16? Anyone? I'm sure you can read well.
I'll read.
Okay, go ahead, please.
Injuries in motorcycle helmet color. Case control or retrospective study was conducted to investigate a relationship between the colors of helmets worn by motorcycle drivers and whether they are injured or killed in a crash. Results are given in the table below based on data from motorcycle rider conspicuity and crash-related injury case control study by Wells et. Some. Test the claim that injuries are independent of helmet color. Should motorcycle drivers choose helmets with a particular color? If so, which color appears best?
Thank you. So you start with null hypothesis, alternative hypothesis. Null hypothesis saying that helmet color and injuries are independent. So injuries and helmet color independent. And then alternative is that injuries and helmet color dependent. So independent and dependent. So step 2 is showing that the expectations are just knowing that the expectation is greater than 5. We just know that after we enter it and they find us B. So we're going to check that. And then let's go and use the chi-square test. Okay, so here is our matrix. I want you to put it into your calculator as you see here. And this is going to be how many rows? 2. How many columns? 5. So 2 by 5. So go to your calculator and see if you can enter it. So go to your calculator. Okay. Second matrix. Edit. And then this time you have 2 rows, 2 horizontal, and you have 5 vertical. So 5 columns. And it should show correctly if you put it correctly up there. 491, 377, 31, 170, 55, 213, 112, 8, 70, 26. Okay, so you entered it here. You don't need to enter anything for B. It's going to generate B later when you call the command. So you go to test, you go to chi-square test, observed A, observed B, calculate. So, and here's the p-value you have. So in order to see if the expectation is above 5, you can go to B now, and then you see that B is all big numbers. Everything is above 5. So going to test again. So chi-square, I lost the numbers. Okay. So there we go. Small p, this is less than 5%. So we reject a null, so reject independence. Support alt, that means supporting the dependence. So you would say there is enough evidence to support that helmet color and injuries are dependent. Okay? Because dependent is the alternative. So let's go to the question. It says, now what do you think, which color appears the best? Means the least injuries. So just look at the list and send me what color. So maybe chat with me. What color, so now that you know it's dependent, what color has the least problem? So send me your answers. Observe the table. Now that you know that they are dependent, means the color is affecting the number of injuries. Tell me which color is the best. If you are wearing one of these, what color would you wear? Excellent, Oyandamala. Excellent, Tammy. Excellent, Andrew. So many of you got it. So yellow and orange seems to have the least. Okay. Any question? So homework is up. Let me just make sure 11.1 homework and 11.2 homework. It shows to be due on Sunday night. And then there would be a quiz activated. So you're gonna have a quiz due on Sunday night and you need to study for the test. Write out the calculator commands. The test is timed. So if you don't write these things, you don't have time to look in your notes. So create a page of note with all these formulas. The exam would be anything after chapter 7. So it would be 8, 9, 10, and 11. 8, 9, 10, 11. Okay. So start from chapter 8 and then a study forward. So one more time, let me just also write it down. Exam will cover chapter 8, 9, 10, 11. Go to each chapter and find sections and then write the calculator command and maybe one example. A2, write the calculator command and one example, so forth. So there would be 3 sections in 8, 3 sections in 9, that's 6 sections. And then 2 sections in 10, 2 sections in 11. So 10 sections in total. It should be simple. Just go to the calculator command and then just know what is null hypothesis and alternative for each one. Now, if you refresh your My Math Lab, you'll see that 11.1 and 11.2 is due on the 18th. And then I will activate the quiz for that by today. It's due on Sunday night as well. That's all. So have a great time. And I will see you on Monday. So work hard. We have just 1 week left. And the project will be up by the end of today on Canvas.